talk is about the project we are currently carrying out, or myself in collaboration with Professor Alois Zeutel at the CPPS lab. And we want to explore the potential of design thinking in cyber-physical production systems. So cyber-physical production systems are enablers for the fourth industrial revolution. So you probably have seen this image in various variations many times. So just to introduce this to you, it's an image that explains how the industrial revolution came about and where it will go. And so we have the first stage where we have the introduction of the steam machine that was later replaced by electrical power, and the introduction of mass production. So as a new paradigm of organizing the production process. Later we had the introduction of IT, and now what is proclaimed as the fourth industrial revolution, we have the introduction of cyber-physical systems in the production process. So basically the transition from the third to the fourth revolution, we have a replacement of a traditional hierarchy of control systems into a decentralized network of cyber-physical systems. So systems or components that can take local decisions, that are intelligent, and that can communicate with each other over the internet, which may involve even the communication across organizational boundaries. So, and also different levels in a hierarchy. So like a hierarchy of processes. So we have business processes that are often located on top. So here we see in this automation pyramid, the enterprise level. So there's a seamless integration from the enterprise, from the business, down to the physical processes. So this makes production very flexible, but at the same time more complex. And this has an impact on the design process as well. So the design process becomes more complex. It involves more disciplines. So it often brings together business people and automation engineers. And there was a study 3 years ago in Germany to identify what needs to be done, what are the main issues in the engineering process of smart products and services, including cyber-physical systems. And among the research needs, this is in German, and I will translate a little bit. So the most important research issues that need to be addressed by 2025 are the inclusion of agile methods into the traditional systems engineering process, and also the inclusion of cooperative approaches, among others. Yeah? So we also see rapid and virtual prototyping. So these are what we have as the primary research needs to be addressed. And this is where I start this project of design thinking. So trying to identify what can design thinking bring to the design process of cyber-physical production systems. Why design thinking? Because it already addresses these issues, but in a different domain. So often design thinking is used in things like consumer products, or also in the domain of how do we solve business problems. So here are some of the key elements in design thinking. We have interdisciplinary teams that work together, that collaborate, and they are co-located in a room, and they have materials like Lego blocks or paper, and they use these materials to rapidly build prototypes in order to increase their understanding of the problem and also, of course, the solution. Yeah? So they build solution prototypes. All this is embedded in a process that's a loosely coupled network of activities that are, where you can iterate easily between these activities. So here we already have these aspects that I was talking about in the context of cyber physical production systems. So we have collaboration, rapid prototyping, and an agile, iterative way of building the prototypes and coming up with a solution. But design thinking has not yet been applied to the world of production, or the application has been only insufficiently researched. So the research question that is overarching in this project is, what are the components of a design thinking methodology that support CPPS design? And what I expect from this project, so the specific results that I expect are, first of all, a framework of CPPS design. So looking more at the theory of CPPS design and how can we locate it in the whole landscape of existing design theories in other domains or in related domains. So design thinking in the here is understood more in the traditional or scientific way as the scientific study of designing. And the next bunch of results is centered around specific methods, how we can support CPPS design with respect to the three issues that were identified and that I presented. So some of the methods we will use are a modular way of architecting CPPS, which facilitates an incremental way of proceeding through the design space. We use tangible modeling, so a way of modeling where you use building blocks, so physical building blocks that you can actually grasp. And well, I will introduce that a little bit later. And finally, the idea of rapid prototyping applied to CPPS, which we will approach by achieving a tighter integration between the modeling and the execution phase, and building mappings between models and executable models. So the first kind of result, or one of them that I would like to highlight, is the integration of tangible modeling environments with the world of production. So here we see a table, and so a tabletop interface where you have building blocks that you can actually move around on the table, and you can use that to build a process model. The advantages of this is it makes the process of modeling more tangible, and you can grasp ideas in a better way, both related to the problem and to the solution. And it's according to our experience, we already have this table in our institute. It creates a more engaging experience of modeling. So everyone is more involved in the process model, and we have had quite good experiences in the past with this kind of model. And we want to use the models created with that to bring this into an environment that's normally used for modeling control systems in a distributed way. So instead of having abstract modeling bricks, you have concrete function blocks. And we want to bring these two kinds of modeling approaches together in order to well, allow for more rapid prototyping, and also to make the collaboration between business people and automation engineers more seamless. And a use case that we want to explore and where we want to do experiments is in the cyber physical systems lab at Johannes Kepler University, to create a use case where we integrate a production process, in this case a MAWAM storage process, where you have conveyors and grippers that sort out different MAWAMs with different flavors, and integrate that into a network of business processes. So this is just one example how we may implement this and do experiments. And how do we analyze all this? Here I'm showing a framework that's based on an existing ontology in design where I contributed in the past. The FBS, or Function Behavior Structure Ontology, which is a way to uniformly represent designs and designing. We extended this a little bit, so we have, no matter what these processes are, so basically the processes are transformations between the different ontological categories, but the important thing is what the categories are. So we have 6 categories. We have requirements, which is the R. Requirements are transformed into functions. Functions are transformed into behaviors. And here we split the behavior into expected and actual behavior. So behavior that is expected from the solution to be produced, and the actual behavior that is exhibited by the solution. And finally, we have, well, structure, of course, so the solution, and a design description that is the documentation of the solution. So roughly, this corresponds to the problem space and the solution space. So you probably heard of this before. So designing is often represented as an interaction between problem and solution. And this is made more, more elaborated with this function behavior structure ontology. And this ontology gives us a coding schema where we can code different design processes, no matter what the methods are and no matter what the domain is of the design. So this ontology has been applied to mechanical engineering, to systems engineering, to service design, software design, team design, even process design. And we will use this to code our experiments of students using different design thinking methods, and also to build a conceptual framework that's data-driven and compare it with different design theories. So this is what I'm talking about. We are using protocol studies where we have controlled design sessions, and we let designers or student designers, in our case, design a solution. We record what they say during the process and also what they document, so what they write on a piece of paper, for example. And we can code this using this FBS coding scheme. So this is an example of, I think this was in the case of a mechanical design problem. And this is just to show you how every utterance can be coded into a uniform code. And in the past, we analyzed this using data science techniques and normal statistical analysis. So here, for example, we have a correspondence analysis of different models of design. So in COSI, so the one that's in the middle, that represents a systems engineering process. In the bottom left, we have RUP, the Rational Unified Process in software engineering, and on the top left, we have models of mechanical and service design. And this is a way how we can locate the different methods on a two-dimensional plane and try to figure out relationships between them and also between the different FBS design issues. Another way of analyzing it is using cumulative occurrence analysis. So here we have on the X, on the horizontal axis, we have basically time, and we count the accumulation of design issues over time. So for every single design issue, we can have different graphs. And so here we see, for example, the light blue line is the accumulation of structure issues, whereas, for example, the green line, that's expected behavior. And we can see a clear difference between the production of these design issues, namely that the structure issues are produced at a constant speed. So we can use all this to compare different models of design and different experiments of design using different methods. So to give you an idea where we are at the moment, what we've achieved so far, so we defined mappings between SPPM, so this way of tangible process modeling, and the production modeling standard IEC 61499. We implemented an interface between two tools that use these different modeling paradigms, and we will implement a similar interface between a different SPPM tool, one that's a bit more applied to IoT applications. And where do we want to go? So we are at the moment writing a project proposal for third-party funding for FFG, and we will publish the results in a scientific paper, but we still have to decide the venue. So this is a summary of my talk, and I'm happy, given that I'm already over my time. I'm